So the title of the talk is Quantifying Interdependencies of Logical Physical Internet Topologies. And let me just jump right in. The research objectives are multiple here. We're trying to do measurement and analysis to enable discovery and fine-grained geolocation of network interconnections. So similar to how IRIS was doing the points of contact between critical infrastructures, we're trying to do the points of contact between networks, all of which we consider today to be critical infrastructures. And this turns out to be really challenging. The internet architecture itself does not have a lot of, let's say, support for measurement. And in particular, measurement between networks. So we can trust that AT&T is doing really pretty good at measuring inside AT&T's network. The problem arises at the points in between the networks where it's not really clear whose responsibility is. And we've seen evidence of a lot of blame shifting, or, you know, it's not my job to upgrade that network when it becomes congested with Netflix or DOS attacks or whatnot. So even building a map of the interconnections and where they are turns out to be incredibly difficult. And then the next challenge is to find out where and what is the cause of performance degradations at these interconnections. So that's the high-level objective of our work. And this actually touches other projects that are at CATA2 that we've been working on for a while, funded by DHS and NSF. So it's a perfect fit for CIRI. I'm really glad to be here. And I'm really hoping to find other people that are interested. And I've heard a lot of talks this morning that talk about very similar words on the slides, just about different critical infrastructures. So I see potential synergies. The problem, I would say, is the difference in this space is it's orders of magnitude more connections between networks than we see with other infrastructures, and it's orders of magnitudes fewer seconds in terms of what's happening, the dynamics. So here we go. So we've, just as a preface, we've delivered two things for this project already, two main deliverables in end of June. And you can get access to both of them. One is work that we did in 2015 on trying to build this map between where ISPs connect, and specifically where ISPs connect at co-location facilities that are not the ISPs themselves, like Equinix, what they call internet exchange points. So we developed a methodology for trying to do that, but then it wasn't clear, and it still remains unclear, how applicable that methodology is to US interconnection infrastructure, which tends to be a little different than other parts of the world, in particular because US networks do not tend to share as much data about who they interconnect with and where. And that's the kind of data that you need to build inferences on. I mean, it doesn't give you the answer, but it gives you a place to start building inferences. However, we do have a facilities map, what we call, where you map each network and where the facility is that they're peering, a co-location facility where networks exchange traffic. And that's all available through the DHS Impact data sharing service platform thing. And then more recently, we delivered something in June, and then we published a version of it at SIGCOM. We tried to apply this and technology building on this map in order to analyze outages that are happening at peering infrastructures. And similar to the water example, these things can have cascading impacts, both within that facility and nearby facilities, or even not nearby facilities, as the case may be. So just a little bit of background, because I'm not sure how familiar folks are. First, let me see if this works. Okay. I'm not sure how familiar folks are with the interconnection ecosystem. There's these things called internet exchange points, which used to actually be points. They no longer tend to be points, and I'll show you an example in a couple of slides. So IXPs provide a place for networks to connect to each other. Either connect to each other bilaterally, just two networks connect, or connect in some multilateral way, like you tell a database at that site, I want to connect to everybody, or here's my policy for who I want to connect with at this site. And so it ends up with many, maybe in some cases over 100,000 peerings at a given exchange point and terabytes of traffic. Some of these exchange points offer pretty meaty service level agreements, like 99.999% uptime, the kinds of stuff that we used to hear about the phone network. It's entirely unclear to me how any of those things are measured. In fact, one of the outcomes of this part of this project is that we don't see evidence that there's 4 or 5 nines of uptime at these facilities. So maybe it depends on uptime of which part of the facility or which router. And indeed, I don't think the networks themselves are in a position to verify that kind of SLA. And then you have something called co-location facilities, which provide the infrastructure for these interconnections. So what's the difference between an IXP and a co-location facility? I'll talk about in a few slides. And both of these are different businesses now. You could operate both. But what it tends to be is that you have people that operate the brick and mortar part, and then you have people that operate the logical layer, and they put routers inside the brick and mortar things. And these are just examples of the SLAs that you see. So outages in these infrastructures turn out to matter. They matter. It might take AWS down for you. It might take your Netflix connection down. And you don't really know where the outage might be. I challenge you in general to find out when you're having a problem with your internet, can you really figure out what the problem is? Generally not. In fact, often your ISP can't figure out what the problem is unless it's inside the ISP. So we believe all this detection of outages is really important to improving situational awareness and transparency and accountability of the infrastructure to begin with. And again, we have other outage detection projects going on at KITA that this project is synergistic with. In fact, one of our challenges is to try to integrate the different pieces of work that we're doing. So how do people do, wow, that's really bad font. Okay, well, you don't need to really know. These are mails from Nanog, or to Nanog, saying, hey, I have some symptom of an outage. Does anybody else have this symptom? Does anybody know what's going on? That's kind of how outage detection analysis is done in the commercial industry today. And of course, not the right people aren't always reading the mailing list or letting you know whether the thing that you're seeing is something that they know about what the cause is. So this is not ideal. And we're trying to figure out, is there a way to improve this practice? Compounding the problem is just how complex these interconnection infrastructures have become. So let me go to the next slide, which is a better example. I'm amazed how fuzzy the slides are up there. Okay. So here is, again, remember I said IXPs used to really be Ps, one point, one building, or a set of buildings right next to each other where networks would come and interconnect. And now they tend to be called IXs, Internet Exchange, because like AMSIX, Amsterdam IX, they may have locations all around the globe. And they support this thing, the term they use in the operational community is called remote peering, where if you have some piece of, if you have a router here, you can basically connect to AMSIX, the Amsterdam Internet Exchange, using layer 2 technology. And you're really as if you're at the Amsterdam Internet Exchange. You can peer with everybody else who's at the Amsterdam Internet Exchange, including all these other people who are doing the same thing. So that's what an exchange point looks like today. So this makes it incredibly difficult to try to infer where a connection is actually happening. Let me give you an example is when you're trying to detect an outage in a path or between two ASs or a facility. So here you got 4 different facilities. These are the co-location facilities I talked about at the beginning. And then let's say you have an IXP who, because it's like AMSIX and it wants to serve customers all over the world and it has the technology to do that at layer 2, it actually operates in several different facilities. You don't necessarily know from a traceroute or a BGP which facility it's operating at. And so let's say you have, let's say, a path between AS0, and AS means, I'm going to use a lot of lingo, so I'll define a few terms just to not freak everybody out. AS is autonomous system. Let's map it to an ISP, almost one-to-one there. BGP is the border gateway protocol. It's how networks exchange information about who can reach what sub-networks of a network how. And then traceroute is a kind of a hack of a tool that lets you, from an endpoint, try to measure, approximate a forward path to another destination by basically lying to the network about what you're trying to do. Okay, so here's a path. AS0, AS1 goes through this facility 2, IXP, and onto, goes facility 2 through this IXP who's operating at facility 2, and then onto AS2. This is what the path looks like before facility 2 has an outage. Bam, power goes out, something happens. So it reroutes, because BGP is super smart that way, it reroutes to facility 1. Notice, however, that the AS path, which is what BGP can observe, has not changed. So the question is, how would you detect a facility at this outage? So what you really need is the infrastructure level path, and we really don't have tools to measure that. I mean, there aren't tools, and as I said, the architecture isn't really amenable. The protocols aren't really amenable to letting you know that information. The TCP IP protocols are really agnostic to what physical infrastructure they're going through. They don't know. They don't even know what network they're in, the protocols themselves. So one, you need to actually capture the infrastructure level hops. Indeed, sorry, I left that out. AS2 doesn't even really know, although it might be able to narrow down whether it's facility 1 that went out, like a power outage at facility 2, or something happened with this IXP in terms of peering, a peering outage or intentional change in peering. If you have enough other measurements of other paths, you could constrain the inferences that you make to hopefully 1 that could possibly be valid. Like here, if you get a path here that you know is going through this IXP, you say, well, I know this IXP didn't go down because I still have a path going through it. So that can let you narrow it down to, let's say in this case, okay, it must be facility 2 that's gone down. Now, if you have enough of these paths, you can do a pretty good job at that. If you have enough of these paths all the time, if you're collecting continuously. So that's number 3, continuous monitoring of the routing system. So this requires the 2 main sources of data about topology are the BGP data, what we call the control plane path. That's what routers have to exchange in order to establish connectivity between networks. And then traceroute, something you can do from the edge or anywhere, assuming intermediate routers to support it, not always. Intermediate routers will respond to your traceroute, not always true. where you can actually try to get a IP level data plane where the traffic actually goes. All right, so the goal here in this new approach to detecting infrastructure level outages, specifically at facilities in this case, is to combine continuous measurement using BGP data with fine-grained topology discovery and geolocation of the topology. So one of the new things we've added in this work, which has turned out to be pretty tedious, is to exploit the semantics of a feature in BGP. Always a good idea to use something that the operators themselves use to keep themselves sane. We've exploited something that the operators themselves use to help understand or transmit where exactly a route is being exchanged. Where is it coming from? So they use something called BGP communities. It's basically metadata they put in the field of the BGP packet. So here, let me give you an example. There's a prefix, just means a set of network addresses. There's an AS path. When you announce what you put in a BGP packet is, here's the prefix I'm announcing to the world. Here's the AS path through which you can get to this prefix behind me. And then you may put a community where the first part is optional. It's a 32-bit value. You can put whatever you want in it. The first part is the AS, the top 16 bits. Second part is what you mean to say, like a message about the route. And indeed, you sort of tag all the routes that have that attribute with the same community. And that's how you know these routes are part of a community. The problem is, indeed, oh, sorry, one more thing. You can put multiple communities. You can put as many communities as you want. You can say, this path went through facility 4, and it went through this IXP, if you want. So you can do quite a bit with facilities. And indeed, ISPs do. When the route changes, your community will change. That all can be automated and configured inside your BGP system. The problem is, these values are not standardized. Different ISPs use different things. There's a few that are standardized-ish, but mostly not. And definitely in the case of how we're trying to use them, they're not standardized. So you've got some documentation in public data sources because ISPs who peer might want their peers to know how they're using communities because it's going to help the peer understand the peering relationships. But in general, you have to go kind of scrape these public data sources and then either on websites of the ISPs or who is information, because sometimes the communities are registered and who is. It's another way to register data about your networks. Volunteer of unvalidated accuracy, like many things on the internet, many sources of data on the internet. So we went and scraped a bunch of these things and did some natural language processing and came up with about 3,000 communities covering 468 ASs. How many ASs are in the internet? About 50,000. So then the question is, okay, how good would this technique really work? Well, we analyzed that. Turns out you get about half of the paths in the BGP set of BGP paths that we observed from public repositories, about a third of IPv6 paths. But importantly, almost all of the facilities that have at least 20 members. So the big facilities do seem to be covered by the communities that we've captured. Okay, so what do you do now if you have this idea? So you have to, first of all, collect a bunch of BGP paths that have these community values in it. Yes?
All the peering happened at a small number of very big things, but
actually, I would say a majority, and people have studied this, OECD has written some papers on this. I think a majority of peering still does happen at facilities like this. However, I would argue, without data, because it's difficult to get this data,
sure, most
of the traffic is not going through those facilities. Okay. Right? So there's a famous quote in an OECD document that says 99% of the peering agreements on the internet are done on a handshake. There's no contract in place. Well, the trick is, if you go to an IXP in Europe, many of these IXPs do what they call multilateral peering through route servers. You go to the IXP and you say, I'll peer with anybody here. So pretty quickly you can get 1,000 peerings. And they have very little traffic going through. So I suspect, although again, it would be good for somebody to validate this, that the vast majority of the traffic going across the internet is going through at least one interconnect that is governed by not only a legal agreement, but an NDA about that legal agreement, that therefore we cannot study it. But yes, great question. And again, and I will say, I mean, you've gotten right to the heart of it, which is, how well does this method generalize? This is still research. We're way on this side of the chasm that Matt talked about this morning. So we're working on that. Okay, so let's give an example. We're studying facility 2. We get all the BGP paths that are going through facility 2. They've got these community facility 2 in them. We gather them, and then we're mapping them. 20,000 paths go through facility 2. We don't care about BGP updates. Each of the messages is called an update. We don't care about updates that even change their community value if the community value still reflects the same ingress point, the same facility that it may be going through. So we go to this. And then, oops, we get some outage, or at least what we see is the facility changes in some of these communities. However, it seems to be only a partial outage. We have a bunch of paths that still do go to facility 2, so we can't say, oh, definitely facility 2 went out. We don't even know if it was a partial outage. It may be that an AS intentionally moved stuff away from that facility for traffic engineering reasons. So we're well into the space of guessing and heuristic, and we do this signal investigation here, which is we do some targeted active measurements from vantage points that we have around the world to try to go through that facility to see how many paths have actually been affected by what we seem to have inferred as an outage, and how disjoint are those paths. So we have techniques, algorithm for going through that, and then of course we can detect the recovery of the outage when the number of facility 2 paths goes back to its normal baseline. So that's a basic technique. It's not that easy, because what might happen is that you have things. Let me just go through this quickly. You have a drop in facility 4. Now we're doing facility 4 paths right here, and you have a drop in those paths, but really it's not that facility 4 had a problem. It's that facility 2 had a problem, and some paths just got rerouted around another facility besides 4 to get to the destination. So you have to if you're monitoring facility 4, you have to also monitor other things. The localization of the outage turns out to be very complicated. So what do you need then? You really need pretty accurate maps, high-resolution maps of where ASs peer, what facilities ASs peer. You can get some of this from public data. PeeringDB is a volunteer place where ISPs will register information about where they have presence so that other ISPs will know, oh, I can peer with that AS there. And then there's other places too. Some operators put it on their websites, so it requires lots of, again, scraping and analysis. But it allows you to decorrelate the behavior of ASs based on where you know that they peer. And this, doing this sort of thing lets you identify not only what facility seems to have had an outage, but how many how many networks were affected at that facility. Again, if you get if you have this PGP data source running continuously, and if you have sufficient vantage points from which you can do the active measurements, targeted active measurements in a strategic way. So we did this, published in SIGCOMM, presented in August, found about 160 outages, most of which were not at least publicly reported in the places that we know about where they publicly mention these things, Nanog and some Twitter feeds and such. And so we did some validation of this, but it's really ongoing work to further test and evaluate this method and hopefully operationalize it a bit and try to get other people to use it. Who do we want to use it? Operators, obviously, colo operators, network operators, regulators are interested in this work. People who are doing infrastructure resilience analysis, and then researchers. The data and the tools we'll make available through DHS Impact, because we recognize, and I think I say it later, no I don't, okay, not on this slide. So what we're going to try to do is make available this BGP community data set that really is the sort of secret sauce of this particular analysis, provide a refined methodology, and then also apply the BGP data analysis, the BGP community analysis, to doing inference of BGP black holing activity. This is when you are experiencing a DOS attack and you ask some third-party service provider to help you absorb the DOS attack by, say, black holing a chunk of your address space so that it routes to null. Maybe takes it off the net so that it's not taking your network off the net. All data will go in impact. So ethical considerations, the obligatory slide here. All of this data so far we're using is publicly available. In some form or fashion that requires a lot of scraping and analysis and derivative data sets. And the derivative data sets can clearly be sensitive. I mean, these are places where it would be good to know what do I have to bomb to take off a whole big chunk of the network? What's the most strategic places to target? So we share that data through Impact. Impact vets the researcher use of the data. If you don't know about Impact, you should know about it by now. All your data should go in there if it's sensitive, or maybe even if not. But I will say, validation turns out to be the other hardest part of this project. And I think that we are going to find, my prediction is that we're going to find this technique is actually pretty hard to do in a validated way with the existing state of data sharing on the internet. So I predict that as this critical infrastructure becomes more critical and we get more infrastructure, we'll need to really confront this issue of data sharing about interconnection data. Even some of the ISPs, amazing, well, I should say the engineers, not the lawyers at the ISPs, are interested in moving toward a place where they can share more data about interconnects. All right, benefits. So we're providing infrastructure-level outage detection methods through public sources, complements other outage detection projects, both in our group and other groups, although I'm very interested in maybe finding other sources of collaboration here. But of course, any quantitative evidence on outages can improve accountability, transparency, and resilience. And that's it. And I have time for questions, I think. Thank you. Thank you so much. Yes.
What were the causes of the outages that you detected?
What
were the causes? Do you know what the main causes are?
Right, power failures. Sometimes, in fact, some of the false positives they got were that there was a fiber cut nearby the facility, but not at the facility. Do you want to count that as a facility level outage or not? It affected many paths in the facility. But often power outages, I don't think so often. One of the questions we've gotten in the past is, what about planned network outages, like maintenance stuff? That doesn't usually affect the entire facility. That usually affects a subset of the networks in the facility. So yeah, I think mostly it's been power outages, and we don't know for a lot of these. Only a fraction of those 160 did we validate with publicly available data sources.
And what were the downstream effects of the outages?
Yeah, we did see some downstream effect. There was a slide in the paper, which I'm a little hesitant to put up, about this proves the SLAs weren't met. Like, definitely we're not talking about 5 nines of uptime at these things, because that's like 20 minutes a year of outages, and we saw much more than that. And we saw evidence through the targeted trace routes, which again, you know, iffy and how accurate you want to claim that latency measurement is, but increases in latency of 100 milliseconds through some paths through this. So, you know, the internet is, architecturally, the routing architecture is incredibly resilient. It routes around. So I don't know that we had places that were totally partitioned and off the net. But certainly impacts on claims about SLAs and latency through the. Great, thanks. Yes, go, Mike.
So apropos of nothing, but that very first slide you have that has, like, it was either peering density or facility density.
Yeah, it's wrong.
Which I've never seen before, which I love. Great. Do you have a sense, again, totally made up?
You mean that?
No, there's no.
Oh, Brad's picture, isn't it pretty?
Yeah. So to what degree does that, do you think, map up to other infrastructure?
Yes, totally. I mean, of course, as
population.
Iris will say, you go where the people are. You take the water where the people are.
Population density,
you take the bits where the people are.
transportation density,
totally.
and power density.
Yeah.
And, yeah.
Maybe even the same road, as you pointed out. Maybe even the same conduit.
Yeah. Okay.
Put all your eggs in one conduit and watch that conduit, right? Well, we don't know. Actually, I mean, I think it's not that case now. I think, you know, only in the last decade have people really gone into this dig once mode where you put everything into one conduit. I think there's still a lot of stuff we don't, and of course we don't know where it is. To the extent that stuff is public records, it's not shared or consolidated in a way that's really usable.
Yeah, I'm just sort of making this analogy for the cyber physical stuff of the separation between control and data planes.
Yeah.
So this idea that as we move to a more cyber physical world, the control plane is going to be telecommunications networks.
Yeah.
And
it is already for the smart grid, right?
And the data stuff is all going to be, I mean, the data is going to be control. Yeah. So like the things one can actuate over the communication network, and so there is no separation. They overlap just like the public internet. They overlap each other 100%.
With IoT, it won't be fiber; it'll be air. I mean, more
sure.
commonly. Although there's always fiber in the backhaul.
Yeah, awesome.
Okay, I think I'm getting gonged.
Any final questions or thoughts?
I'll be around. I do have to leave at 4:30 today. I won't be at dinner, so come find me if you think we should. If there's somebody I should know, I'll talk to. Thank you very much.